guys. Convergent plate boundaries. This is where plates come together, and so these are divided into 3 different groups based on, not like divergent plate boundaries, the stages or the time of which they've occurred, but the type of crust that's involved. So the first one is ocean-ocean convergence. This means you have 2 oceanic plates colliding together. And when that occurs, whichever one is usually colder and older and denser is going to sink down below the other. Marianas is a perfect example because this crust is so old. Go back. Marianas Islands. Okay, here we go. So we're looking at some really old crust, about the same age as here on the edge of North America. In fact, there is some speculation that this part of going off the east edge of North America is becoming so old and cold and dense that it's beginning to sink down and may start a subduction zone forming, which means the future of the east coast of North America will be more volcanoes, like has been. You know, the Appalachians have been volcanic in their history. But that's really cool. Once we have very old, cold, dense oceanic crust, it can begin to sink, and maybe we're starting a new subduction zone here. I don't know. That's pretty cool, and we won't be around to see it, but geology is neat because we're only here for a snapshot. We're only here for a tiny period of time, and we're seeing all these things at all these different stages of their happening, but we're only seeing them. It's like a glimpse. It's like owning a dog, right? You have that dog for 15 years or so, and he doesn't understand your whole life, right? He's only seeing a little snapshot of it. He has no idea that you're living for 80, 90 years, whatever. He's only seeing his little part of it. That's like us looking at the planet, but way bigger because we're looking at billions of years. Anyway, it's kind of a dumb example, but just popped into my head. My dogs are getting old, so I was just thinking of that. So we have some old, cold crust here with the Marianas, and as it's sinking, it's driving a lot of old oceanic crust down with it, again, making the deepest part in the ocean, the Marianas Trench. And, as this is going on, we're also eventually going to get remelting of crust. So we have melting happening deep down here, a lot of processes. What's happening down here is a whole party of fun stuff that we'll talk about next week. That's a fun topic. But anyway, as this is going on, we're creating volcanoes. So then we create a chain of mountains that are volcanic. People can go and live on these things. This is what Indonesia is, and the Philippines, and Japan, and the Marianas Islands, and the Tonga Islands, and that little chain off of Alaska, the Aleutian Islands. This is what they are. They're volcanoes forming from oceanic plate diving down under another oceanic plate. There should be no land there, but there is because of these volcanoes that are very explosive, very deadly, but it's a place to live. It's land, right? These islands wouldn't exist if it wasn't for this process. Okay, similar, except now we have a little less controversy over which plate is going to subduct, because when an oceanic plate collides with a continental plate, only one thing can happen. The oceanic plate is denser than the continental plate, so it's always going to sink below it. Continental crust does not subduct. I don't think there's anywhere on the planet where it's being pulled down and actively remelted on a large scale. It floats, it sits there. The oceanic plate is the one that recycles down like the edge of a conveyor belt. So, but you get this similar thing going on. You get volcanism, and now instead of a chain of islands, like an oceanic island arc, like we just saw happening in the oceans, we are getting a chain of volcanic mountains forming on a continent. So the Andes are a perfect example of this. So we have subduction taking place. We're creating mountains here, and these mountains are volcanoes. They are very active volcanoes too. Something similar is happening in the Cascades. So as this big subduction zone is occurring off the west coast of North America, we are creating things like Mount St. Helens, Mount Rainier, Mount Hood, Mount Shasta, all these active volcanoes here in the west, on the west coast of North America, all the way up through Alaska too. Okay. Oh yeah, cool video about this one. I think was really helpful. And again, this is that earthquake science playlist that I linked to in the, you know, in my lectures. So it should be right above this video. Please, you know, just have fun. There are a lot of these videos and they're all very short and very, very helpful. And I think they do have narration too, but okay. So here we go. We have an oceanic plate and is diving down below what looks like to be a continental plate. And we've got some things happening. We've got kind of like a bugs on a windshield thing where we have some stuff being scraped off the oceanic plate and being squashed up onto the continent. We're getting a four-arc basin here, so we have some, you know, range being uplifted, but then inland we have down dropping, so that's kind of cool. But ultimately, what we're dealing with, oh, earthquakes, oh yeah, tsunami, okay, talk about that later. But we're also looking at melt eventually, so as this plate is descending down, we are getting melt happening, and we're getting volcanoes forming. So that's what's going on at a subduction zone. Lots of fun stuff. Yeah, so usually when you hear about things happening in the news, like a devastating, you know, earthquake happening anywhere on the earth, except for Yellowstone, those are different. We'll talk about that a little later. Usually though, they're happening at subduction zones. So this is where a lot of fun stuff is happening. Not fun stuff, I don't wanna say that. The most, you know, the most deadly natural hazards on the planet happen at subduction zones, probably especially tsunami. But still, for a geological perspective, it's, you know, it's interesting. Okay, just a taste of what's happening down in that subduction zone there. We'll talk more about this in a couple weeks, but as that rock is melting deep in the subduction zone, well, it's bringing a lot of stuff down with it. It's bringing down water because it's been at the bottom of the sea for, you know, a very long time. It's bringing carbon. We'll figure out a little bit later why, but think about where that carbon could come from. But next week we'll get into that more. So we're getting all this stuff happening in the subduction zone, and that means that we're building up gases because this stuff is being heated. We're creating gases behind this magma. So that means that we have some of the most explosive volcanoes on the planet. This is a picture of Mount Pinatubo, which erupted in 1991. This is in the Philippines, so a perfect example of an oceanic subduction zone. Or if we don't really have the explosion, if we're just seeing the eroded remnants of one of these bodies of rock where magma was kind of injected into the continent and, you know, we're not really seeing the volcanic part of it, we can look at what's called a batholith. And this is going to be, we'll get into this more next week with igneous rocks, but this is going to be a body of magma that cools and solidifies in the earth, and, you know, like a big body of granite or something like that. Okay, well, who cares? Well, we don't really see that until a long time after this is no longer active and it's been uplifted and eroded, and then it's a big body of granite for us to look at and mine and use for our countertops or whatever, and or climb, like Half Dome at Yosemite National Park in California. So whenever we see granite mountains, that's how they form, is again from this same type of situation, subduction. Okay, the third type of convergent plate boundary. Now, we are not recycling any crust. Nothing is diving down here because we're not looking at oceanic crust. We're only looking at continental rock. Continental rock, as you know, being made of granite, is buoyant. It doesn't want to dive down into the asthenosphere. When they collide together, there's not going to be a lot of, well, the root of this whole system does get thicker and thicker, but mostly the movement is skyward, right? So we're going to build some of the tallest mountains on the planet because these lightweight continental rock bodies are going to squish and start to go vertical. We do build a thick root though. Recently we found out that the depth of the continental rock below the Himalaya mountains is at least as deep as the Himalaya mountains are tall, right? So we're not just building high. We're floating. You know, the continental rock is floating in the asthenosphere of the mantle. It's not all going to go up. It's going to kind of find a equilibrium there. But the Himalayas are an excellent example of where we can see this happening today. And we could go here to Nepal, Tibet, India, you know, these countries that have the Himalayas, and we can actually measure the Himalayas rising every year. After Nepal had their big, devastating earthquake a few years ago, a big part of the Himalayas actually dropped by a couple inches, whereas other parts were uplifted. And the Himalayas do rise at a rate of, I believe, is about an inch or two a year. Again, slow, but hey, over 40 million years, which is what it's taken for these, you know, we have the tallest mountain system on the planet, which is very special. So the Himalayas are a great example, as well as the entire Tibetan plateau behind it, extending even up into China and towards Mongolia. So we have an immense amount of rock just being uplifted here and buckled, and is the tallest on Earth. That's pretty impressive. What's also very impressive is the Appalachians also formed from this kind of process. So we'll talk about the Appalachians more toward the end of the semester, because they're actually involving most of the processes we've just been talking about. They're pretty complicated.